Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 8.1, day 2, entitled Polar Coordinates. And today we're going to finish talking about converting between polar and rectangular coordinates, but we're going to focus more on dealing with that conversion in an equation format. So we're going to take an equation that's written in either polar or coordinate or rectangular coordinates, and we're going to convert it to the other one. So this is kind of funky. The solving strategies for this aren't necessarily as structured or as rigid or as what you're used to when you are dealing with algebra or algebra 2 equation solving. So I'm going to show you some techniques that will help you so that you can see the different strategies and how solving for R basically in a polar form is just a little bit different than solving for X or solving for Y. So here in example 5, we have the equation x squared equals 4y, and that is a traditional rectangular equation. If we solved that for y, that would be a parabola. Okay, and we're going to convert it now into polar coordinates. Okay, so we have to remember that, let me switch colors here. We have to remember that x in rectangular form is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Now we also have the equation x squared plus y squared equals r squared, but we're not going to need that so much for this particular example. But these two equations that we were talking about in the previous section of notes, we will need those to do this problem. So if we're dealing with x squared right here, we have x is r times cosine theta. So what we're going to do is we're going to substitute the r times the cosine theta for the x. And we're going to do that for the y as well. We'll leave the 4, but the y we're going to replace now with r times the sine of theta. So I'm switching out those rectangular coordinates and I'm putting in the polar value for those coordinates. Okay, now on the left-hand side, I have r times the cosine theta, and it's squared. So basically, I can square each of those terms. I can square the r and the cosine theta. There's multiplication going on here, so this is where I can just kind of distribute the exponent to each part of the term. I don't have to worry about foiling because there's no addition or subtraction. And then I'll have my 4r sine theta on the right side. Now, when we're solving for polar coordinates, we have to solve for r. And when you're looking at this type of an equation, you have an r squared on one side and an r on the other. Now, if this was algebra, we'd want to get all the variables on the same side. We'd want to try and take out a GCF or something like that. We'd want to maybe factor if we have an x squared and an x, okay? But for the polar, having an r squared on one side is kind of a clue that that's the side we want to simplify and solve for r on. So I want to change this r squared into an r. And you might say, oh, I can take the square root, but that just kind of takes us back to where we were. So the other thing we can do is to get r by itself, we could divide by r. So that way I have one r left, but I need to get r completely by itself. So I'm going to divide by the cosine squared theta as well. And what I do to one side, I have to do to the other. So this is kind of a new technique. This isn't something that's intuitive necessarily, but hopefully now that you've seen that, you realize, oh, okay, so the cosine squareds over here are going to cancel. One of the r's is going to cancel, so that will leave me with an r on the left-hand side of the equation. Now on the right-hand side, I also have the r's that are going to cancel. So I end up with 4 sine theta over cosine squared theta. Now that is a trig expression that I can simplify down a little bit more. And to help me do that, I'm going to break it apart so you can visualize it differently. I'm going to leave the 4, and then I have the sine theta over cosine theta, but then I also have another cosine theta. So I'm going to kind of break it apart into 3 little terms here. And the reason I want to do that is I want to isolate the number here. So I have the 4 over 1, so that's just going to be a 4. But if I put a sine over one of the cosines, that can switch into tangent. And then this other cosine in the denominator, the 1 over cosine, that's actually secant. So that would be my final answer then for r. So that would be what I would have to graph on a polar coordinate in order to get the same shape that I would in the rectangular coordinate. Now in section 8.2, we're going to talk more about how to actually graph in polar coordinate systems. So that's coming up. So for now, we're just practicing this converting back and forth. Okay, so let's try another example here. This one's not in your book. We have x squared minus y squared equals 1. It looks very similar to a circle equation. If it was x squared plus y squared equals 1, we'd have a circle. Okay, but again, I have to use my knowledge of what x is and what y is. Okay, so I'm going to substitute those values in first. So I'm going to replace x with the r times the cosine theta, and I'm going to square it. And then my y is r times the sine of theta. I'm going to square that. So now when I square each of those, just like before, since there's multiplication here, I can just kind of distribute that squared to my terms, or square both of the terms. Oops, that's a minus. R squared sine squared equals 1. Okay, so now, if you're trying to think of what do I do next, if you look at both of these terms, I have the r squared cosine squared and the r squared sine squared. Both of them have an r squared. So I can still take that out like a GCF. Okay. Now, this cosine squared theta minus the sine squared theta, that's actually part of one of our double angle formulas. Our double angle formula, double angle, I'll just abbreviate it, for cosine 2 theta is actually cosine squared theta minus sine squared theta. So if you have that little formula sheet still, or if you remember that, you'd have to know that. You'd have to remember that this looks familiar and recognize that, oh, cosine squared theta minus sine squared theta is really cosine 2 theta. So I'm going to substitute that in now too. So I have r squared times cosine 2 theta. That's equal to 1. So now I still want to try and solve for r, but there's no way that I can really get r by itself here. I can get the r squared by itself if I do 1 over cosine 2 theta. And technically I could get the r by itself if I took the square root, but we don't need to do that here. Okay, we can just leave it r squared. And then this 1 over cosine, I can simplify that down further and make that secant. So I could have secant of 2 theta. Now, if I wanted to solve for r, I could say r equals plus or minus the square root of secant squared theta. But this is fine for now. Okay, since these are the only r terms that I have, I can just leave it r squared. In the other example though, since I had an r squared and an r, divide by that r, so that way you have one r on one side and then the r's on the other side cancel. Okay, so that's just an example of how we can take out a GCF and how we can use some of our previous knowledge from Chapter 7 to rewrite the expression and simplify it down. Now, in these examples, you want to think of these graphically, because we're really familiar, I hope, with the equation y equals negative x, or even just y equals x. Okay, that's just a line, good old slope-intercept form. So if I just thought of that mentally, just made a picture, okay, that's this line right here, y equals negative x. You start at 0, 0, and you go down 1 and over 1, down 1 and over 1, down 1 and over 1, down 1 and over 1. Okay? Now, that, if it was graphed on a polar system, or a polar coordinate system, would look kind of familiar because it's, it's kind of like a distance and a certain angle that we'd have to go around the axis or the pole. So if we look at this graph, we look at it from left to right. Okay, so this line is going down. So if we just look at this part right here, if that part was a segment and it had a point on it that we had graphed, we could think of what radian that theta measurement would be. So as we're graphing, since our slope is 1 over 1, we know we're going down the middle of this quadrant, right through the middle. So that's that pi over 4 value. But we're in the fourth quadrant, so this is really 7 pi over 4. And for part B, here we have to convert theta equals pi into rectangular. So now the other ones we've done, we've switched them all to polar. Okay. This one though, here we have the equation theta equals pi, and we want to switch it back into rectangular. So again, let's graph where theta would be. Theta equals pi, that would be over here. Okay. Now, it's going to be a line, though, in the rectangular coordinate system, so it would go back to the right as well. And that line, I hope you know, is y equals 0, the horizontal line. Okay, so some of the examples that you're going to see in your homework, you can just think of them graphically, especially if they're real simple, straightforward, slope-intercept form type of rectangular equations, or if they give you an equation that's theta and an angle, basically, plot that and see if it looks like a straight line, either straight horizontal, straight vertical, or this one that has a very obvious diagonal direction that has a very clear radian measure to it. So for some of those simple ones, graph them first, draw that picture, and then see if you can write the equation for it. Okay, now example 5, or I'm sorry, example 6. This is our last example, or last set of examples. We've got A, B, and C. And we're going to change these polar equations into rectangular ones. And there's a couple of them that we can actually graph as well. So that's why it says, if possible, determine the graph of the equation. Now, for part A, I have r equals 5 secant theta. Now, I have to remember that I've got x equals r times the cosine of theta. I also have y equals r times the sine of theta. And then our other equation is r squared equals x squared plus y squared. So that's how we're going to convert back and forth between rectangular and polar. We also have the tangent equation, but we're not going to need that for these problems. Okay. Now, secant, hopefully when you look at that, you think, oh, secant, that's really 1 over cosine. So I'm going to make this 5 over cosine theta. So now I have a cosine in there, which is helpful because this first equation is r times cosine theta. So if I can somehow get the r times the cosine theta, I can substitute in the x, and that'll help me go from polar into rectangular. So you have to say, okay, can I multiply the r times the cosine theta? And if you think of it as a proportion, you certainly can. You certainly can multiply the r and the cosine theta. So if we have r times cosine theta equals 5 times 1, which is really just 5. So that r cosine theta is equal to 5, and that r cosine theta is also equal to x. So this is my rectangular equation, and remember that's just a line. I think I have more room on the next slide here. So if I have x equals 5, if you go to graph that, 1, 2, 3, 4, 5, you're going to have a vertical line. Okay, so that's pretty cool that x equals 5 is the exact same thing as 5 secant theta on a rectangular or on a polar graphing system. Okay, so let's take a look at part B. Maybe if I can switch pen colors here. Maybe not. Okay, part B has r equal to sine theta. Alright, for whatever reason it won't let me switch colors. So we will just go like this then. Alright, so I have 2 sine theta, and I have an r. There's really no way that I could multiply the r and the sine theta so that I would get r sine theta to be able to substitute in a y. So I can't really do that. I don't have a cosine, so I can't really use that first equation either. This other equation has me needing an r squared. Now if I could change the r to an r squared, I could maybe work with this a little bit. So here's what we're going to do. I'm not just going to square both sides because I don't want to deal with the sine squared because that's just going to complicate it some more. So what I'm going to do to change this r into an r squared is I'm going to multiply by r on both sides. So that'll get me r squared equals 2 times r times sine theta. Okay, so that's legal. That's a legal math thing to do. You can multiply both sides of an equation by something. You just made it r times bigger. Okay, it's just like you put in a GCF instead of taking out a GCF. But now this helps me do 2 things actually, because now I have an r squared that I can substitute, and I also have an r sine theta that I can substitute. So that r squared is going to be x squared plus y squared, and then the r sine theta is going to be y. There we go. Now it's all rectangular. Now I can still simplify this and clean this up a little bit. So if I get all my terms together, minus the 2y over, then I have these y terms here. Now, I can do something with these y terms. And you have to kind of remember way back to your factoring days when we were completing the square. Because I have an x squared term, so this is kind of like x plus 0 squared. But these 2 terms, if I took that binomial and completed the square, I could make it into a perfect square trinomial. So I'm going to take half of the 2, which is 1, and square it, which is 1. So I'm going to add that in to both sides then. 0 plus 1 is 1. I can write 0 plus 1. So now these three terms here are going to be factorable. So I'll leave the x squared, but I'll write this as y minus 1 squared. Now that hopefully looks familiar. Okay, that's going to be our final answer. And that's actually an equation of a circle. Let me finish this up on the next slide here where there's a little more room. If I have x squared plus y minus 1 squared equals 1, remember this x is the same as x either plus or minus 0, however you want to think of it. And remember those values in with the x and the y, they tell me the center of my circle. So my center is going to be 0, 1, and then this on the right hand side, this 1, that's my radius. If I take the square root of that, I get 1. So if I was to graph this, I would go to 0, 1, and then I'd have a radius of 1 all the way around. So when I graph it, I'll have a little circle. Now that's a pretty sloppy circle, but that's what that equation represents. So that's kind of cool that if you graph 2 sine theta, it makes a circle. And again, in section 8.2, we're going to see how that actually works out. Okay, still can't switch colors for whatever reason. Okay, so let's draw another little line here and let's take a look at our last one. Now this one is going to get pretty messy. It's probably the most complicated one here. It's not going to be easier to graph in the rectangular form. It's actually easier to graph in this polar form. And you'll see that after we get it all simplified down. Okay? But if I'm looking at this, I have r equals 2 plus 2 cosine theta. Again, if I had an r times the cosine theta, then I could substitute in an x. If I had an r squared, I could substitute in the x squared plus y. So kind of like what we did in part B, I'm going to multiply every single term by r. That way I'll get the r in there with the cosine, I'll get the r squared in there. So I'm going to multiply by r, but remember you have 3 terms here, so we have to multiply this 2 by the r as well. So now I'll have an r squared, 2r plus 2r cosine theta. Now the r squared I can replace with the x squared plus y squared. The 2r I can't really do anything with. Now I know I have a 2r and a 2r, so sometimes students see this and they think, oh, I'll take out a GCF. But that's not going to help you get rid of that cosine. We got to get that cosine out of there. So this r cosine theta I want to substitute. So I'm going to leave the 2r for now, and I'm going to replace the r cosine theta with x. Now, that r is still an issue. I got to get that out of there if I want to really have a true rectangular equation. So I'm going to subtract the x, or the 2x, over to the other side. So I have my x squared, and then my y squared, and then minus 2x. Okay, so then we'll have x squared plus y squared minus 2x equals r 2r. Now, I have to get rid of that r. So now that I have it isolated, I have to finish getting rid of it. And again, the way to get rid of it is to multiply by r, okay? But if I multiply by r like we've done up at the beginning of example C or in example B, if I multiply by r, that'll get me an r squared, but then I'll also have an r with the x squared, and an r with the y squared, and an r with the 2x. So multiplying by r will get me the r squared, but then it's going to get me more r's on the other side. So the other strategy I can use to get an r squared is to square both sides. Now, this term over here, I'm not actually going to FOIL this all out or distribute this all out. I'm just going to leave it x squared plus y squared minus 2x squared. Just leave the whole thing squared. And now I'll have 4r squared. And now that r squared, then I can replace with the x squared plus y. So again, I'll leave this x squared plus y squared minus 2x, whole thing squared. And then I'll have 4 times x squared plus y squared. So now I've gotten rid of all of the cosines, all of the r's. I had to multiply by r, I had to square stuff. And so now it's all in rectangular form. And I know it doesn't look clean, it doesn't look neat. If we were going to actually graph this, this would be very complicated to graph in a rectangular form. So this is the proper rectangular form, but to actually make a graph for this one is not going to be possible for us. It's actually easier to graph it in the polar form. Okay, so this is another advantage of having another system to graph in, because things that are complicated in a rectangular coordinate system can be really, really easy in a polar coordinate system. And again, we're going to talk about how you can do those types of graphs in section 8.2. Okay, so this was the book graphs that I drew on the previous slide for part A and part B. And this is your homework to practice these concepts. You definitely want to practice these. Okay, look in the back of the book at the answers because they're all odd. You can see the solutions worked out in the binder in the classroom or on the class website. And if you have questions, come on in and ask. This is definitely stuff that I expect you to have questions on because these problem-solving strategies are a little new. They're a little different than what we traditionally do when we're solving algebraic type equations. So sometimes it takes a little while, it takes a little practice to figure out when do you square stuff, or when do you solve for r, or how do you solve for r, or do you multiply by r. So practice these problems so that you get a better sense for when to do those strategies, but definitely ask questions on this as well.